Okay, we are in 2.5, nearing the end of the chapter. And this section is all about limits involving infinity. Alright, we're going to look at two real-life cases and look at the graphs and check out the limits. Our first case, we're talking about generic town A. They have a need for more doctors. The town's growing and growing, and as the population grows, they need more doctors. So more people know that there's a need for doctors, so they go into the doctor field. And then what happens is too many people start going into the doctor field for this town, and then people, because they know they can't get a job in it, then they stop going into the doctor field. And this cycle just keeps happening. Pretty soon there's a shortage of doctors. Then more people get in, then there's too many, and there's shortage, and pretty soon it zeroes in. So what we have happening is town A has a need for more doctors as the population grows. Then pretty soon there's too many doctors. So people stop going into that field. Then there's too few doctors. And this cycle keeps repeating, and it kind of looks like this. So our x-axis is going to represent time in years, and our y-axis is going to be the number of doctors in this town. So we'll put this at 1,000 right here. So at the start, there's not enough doctors for a population, so the doctors are below where we want them to be. So everybody goes in to the doctor field, and pretty soon we've flooded the market, so nobody starts seeing a doctor, and then they start to decrease, and pretty soon they're too low. Then more people come in, and you'll see this in the job world. It gets flooded, then there's a shortage, flooded, shortage, flooded, and pretty soon it zeroes in on where it needs to be. Just naturally happens. So we've crossed this line right through here many, many times. I'm going to hit all those. So when with a graph like this, I can ask the question, what's the limit as time approaches infinity of this doctor function? And if you look, it's the y value that we're approaching. We keep jumping up and down across it, but what do we approach as time goes on? We zero in on that 1,000. So here, instead of approaching a single x value, it's the idea of going all the way out to infinity. And what y value are we approaching? That's our limit. So we got 1,000. Another way to involve infinity. Okay, let's say we've got a flashlight pointing at a wall. And we're going to be measuring the length of the beam of light. Measure the length of the beam, of the light beam. Then you're going to rotate your hand upward. Which in point rotates the flashlight upward. And we're going to look at, as I change the angle of the flashlight, what happens to the length of the beam of light. And if you think about our domain here, our domain can only go up to that 90-degree spot. So we're only looking at this function from 0 to 90 degrees. And in calculus we work with radians, so just a quick review. 0 degrees is still 0 radians. And remember, all the way around a circle was 2 pi radians. Just real quick here. All the way around is 2 pi. Halfway around would be pi. So that puts 90 at pi over 2 radians. Okay. So our graph would look like this. Let's go pi over 2. And let's say I'm starting at 5 feet from the wall. So if you need a little picture, here's my wall. Here's my little flashlight. Little button, the beam of light. That's a bad flashlight. Okay, and we're starting 5 feet away from the wall. Now we're going to rotate that flashlight up, and as I rotate it up, the beam of light is going to get longer and longer and longer and longer until my flashlight is pointed directly parallel to the wall, which is at that pi over 2 angle, and we'll show that. So if you think about it, when I get to pi over 2, if I had a strong enough flashlight, that beam of light would go up forever. So when I'm at my 0 radian angle, I'm at 5 feet, and as I increase the angle, my beam of light gets longer and longer and longer. And like I said, if my light had enough power, that beam of light would go up and up and up and keep climbing all the way to infinity. So now I can ask a question. If I ask for the limit as, what do we want to call this? The angle, let's call x. X is the angle. As x approaches pi over 2 of the length of the beam of light, normally we would say, because my 2 fingers aren't coming together at a single point, we would say no limit. And you're still correct. But what mathematicians do is we know what's going on here. This beam of light is going to be infinite in length. So they say that the limit is infinity. And the reason they do that is it describes what's happening. When you say the limit is infinity, you know the graph is going off up into infinity. So at this point, we're not going to say no limit anymore. We're going to say that the limit is infinity. So, because it's describing the behavior. So, technically, there is no limit, but we are going to say the limit equals infinity because it describes the behavior. So when we say the limit's infinity, we know the graph is going off into infinity. Okay, now we're going to look at properties of limits involving infinity. So we will look at a function equal to 1 over x minus 3. Right away, that denominator, you can see there's going to be a 0 down here, so we're going to have something happening, something undefined. Let's take a look at the graph. Divided by, the bottom has to be in parentheses, x minus 3. X minus 3, I'll do a zoom 6. And we want to keep our eyeballs on that x value of 3. Well, there's the 3. We've got a vertical asymptote happening there. So the branch looks like it's approaching the x-axis on the bottom side here, and approaching the x-axis on the top side here. So at 3, you have that vertical asymptote, your imaginary line, not a part of the graph, just what you approach. And then we've got these two branches. Looks like this and this. And it really looks like the x-axis is a horizontal asymptote. We get closer and closer to the x-axis too, but never cross over it. So two asymptotes in there, one vertical, one horizontal. Now, two different cases to look at inside of this. As x approaches infinity, we want to look at the limit as x approaches infinity. And then just from the graph, let's see if we can get this limit. And we're talking positive infinity here, which means I'm going to have to be over on this part of the branch. As I approach infinity, what y value does it appear that this graph is getting closer and closer and closer to? Well, if you think about it, this arm of the graph is going to drop closer and closer and closer. What y value is this along the x-axis? It's a y value of 0. Okay, let's look at the limit as x approaches negative infinity. Well, to get on the branch where the x value is going out to negative infinity, that's over here. And you can see as I go out farther and farther to the left, this graph is going to keep climbing up and climbing up, but getting closer and closer to this x-axis here, but that x-axis still has a y value of 0. So, how could we have gotten these answers without looking at the graph, in case you have to do that next year? Well, in general, what we're going to say is if the function takes on the form 1 over infinity or 1 over negative infinity, we're going to say that both of those, it's like taking the number 1 and dividing something enormous into it. How many times is something enormous going to fit into 1? Not at all. That's why they're coming out equal to 0. So if you get a 1 over infinity or a 1 over negative infinity, the answer is 0. The limit will equal 0. So, if I look back and I try to redo this without looking at the graph, just by substituting infinity in for the x, I'll show you what happens. You get the limit as x approaches infinity of 1 over infinity minus 3. Okay? Infinity minus 3. Think of infinity as all the sand on the beach across the world, minus 3 little grains of sand. Okay? So what do you basically have down here? You still have all the sand in the world. You still have infinity. So this is 1 over infinity, which is where we can say we got 0. So we can do it algebraically without looking at the graph, just by substituting infinity in for the x. And then this function takes on the form 1 over something enormous, 1 divided by something enormous, doesn't fit in at all, 0. Same thing with the negative infinity. We go positive and negative here.